In the beginning, there was nothing. But what's your concept or idea of nothing? You probably, in your mind, you'll imagine empty space, a vacuum, empty space devoid of any particles. But the strange world of quantum physics has forever changed our concept of nothingness, of empty space. We now know that empty space there's actually a lot going on. There's these virtual particles popping in and out of existence. So virtual particles, it's particles and antiparticles. So think about a 0 and then a +1 and a -1. So out of 0 you can get a +1 and a -1, a particle and its antiparticle popping out of nothingness, out of 0. And then again, if they touch each other, they annihilate. So +1, -1, it's 0 again. So in empty space, we actually have these virtual particles always popping in and out of existence. It's a bubbling brew of this going on all the time in empty space. So this video I have here, this is a simulation done by smart scientists. If I remember correctly, this was presented at one of the Nobel Prize Awards for science. Anyways, it's a simulation of the inside of a proton. And this is actually the simulation of the virtual particles popping in and out of existence all the time. So you can see it's really, really busy inside a proton, inside empty space. These quantum fluctuations, as it's called, is responsible for more than 90% of the mass of the proton. We can predict with this model and measure quantum parameters to the accuracy of 1 in a billion with this model of virtual particles. So an accuracy of 1 in a billion because of these virtual particles. They explain certain parameters of elementary particles. So they exist. There's no question about it. We know they exist. But okay, back to a story of creation. Oh, well, not creation, the story of the birth of the universe. So you can also imagine that we have virtual particles in empty space popping in and out of existence, but we can also actually have space itself popping in and out of existence. So imagine space being the matter being space. You need space to have particles, you need particles to have space. So space can actually also pop up into existence like these virtual particles, this quantum fluctuation. In the strange world of quantum physics, most of this is possible and is actually happening. So now imagine a piece of space popping into existence with particles and antiparticles, and then all of a sudden, bang! Okay, it's maybe more like a big pfft than a big bang. But imagine, this is called cosmic inflation. So imagine we have this piece of space popping into existence for a short while with particles and antiparticles, and then there's inflation. So inflation refers to this piece of space growing really large, really fast. Okay, we're talking crazy numbers. So it was really small, smaller than a proton, and it grew larger than a basketball or football, soccer ball in a very, very short time, a fraction of a blink of an eye. So if we talk numbers, in as short as 10 to the minus 32 seconds, 10 to the minus 32 seconds is 0.00000000000000000000000000001 seconds. It grew a factor of 10 to the power of at least 26. The conservative estimate is 10 to the power of 26, but it can go up to 10 to the 90. I'm not going to count that again, but you can imagine 10 to the 26, that's a 1 with 26 zeros, or 10 to the 90. That's how big it grew in a really short time. Now that's cosmic inflation, or what I like to call the big pfft. Anyways, when this happens, these quantum fluctuations sort of got frozen into space. So imagine these virtual particles, we had antiparticle particles, and then inflation, this cosmic inflation happened. And these particles then all of a sudden, so space grew very large between two of them, or more of them. And they were too far away from each other then to annihilate again. And so we have space with energy. And that's the birth, the start of the universe. So also at this stage, when inflation happened, and depending on the randomness of quantum fluctuations and these virtual particles, that's also froze into space the properties, the properties of our universe as we know it. It's a function of the randomness of these quantum fluctuations. That's why the cosmic parameters, cosmic numbers, they seem so random, and it's maybe because they are random. Because of the randomness of quantum fluctuations, then we had inflation, and that established these parameters, and they got frozen into space-time. So now we have space. It's kind of the birth of space. It spawned, not created. I hate that word. Spontaneously began. Okay, so we have space, and because of this initial momentum, it continued to grow. There was energy, and space continued to stretch and grow. Sorry, I need this. Okay, but in this early stage, there's a lot of energy. Again, think of energy as heat. Energy equals heat, heat equals energy. There was a lot of energy, a lot of heat. So much so that your normal particles couldn't form atoms. So what I mean with that is electron couldn't bind with a proton to form an atom. There was too much energy. The energy sort of ripped it out of this orbit around, in the classical way of thinking of an atom with a proton and electron. It couldn't form. No atoms formed as the electrons moved around freely. There was too much energy. There was even so much energy and heat in this early universe. The universe was in a hot, dense state, according to the Big Bang theory, the TV show Big Bang Theory. The song, the universe is in a hot, dense state. Anyways, hot, dense state. And it was in a state of plasma. So plasma is thought to be the fourth state of matter. So we have gas, liquid, solids, and then plasma. So plasma, if you take a gas and you add a lot of energy, so the electrons sort of strip away from the rest of the atom, the nucleus of the atom, and it moves around freely. So it's so hot and dense that even photons are the little packets of light that we need to see. They couldn't move around freely, so the universe was opaque. Photons couldn't move. Universe was opaque. Anyways, the universe continued to expand and grow, and then at one stage, approximately 380,000 years after the big the universe cooled enough, expanded and cooled enough to about 3,000 Kelvin. Kelvin is a measure of temperature related to degrees Celsius. So let me get this wrong. Right. 0 degrees Celsius is 273.15 degrees Kelvin. So when the universe cooled to 3,000 Kelvin, it was cool enough for atoms to form. So finally, the electron can bind to a proton to form hydrogen. And this also meant that now the photons, these small packets of light, were able to finally freely move around without being absorbed by all this energy. And the universe became transparent. So I want to show one of the most amazing, coolest pictures ever. So because the universe became transparent, we could start to see, so light, photons could freely move around now. We can take a picture of the universe at that stage. So because the universe stretched now for 13.8 billion years, that's when the Big Bang, how long ago the Big Bang was. So 13.8 billion years ago, we had the Big Bang. 380,000 years after that, the universe became transparent, and we have a picture really honestly a picture of the early universe taken by the Planck telescope. So it's quickly just if you look at a star, let's say that the star is 4.2 light years away. That means it takes the light 4.2 years to travel from there to our eyes. Similar with the picture I'm going to show now, it's literally light waves, electromagnetic waves that traveled 13.8 billion years. And we can take a picture of that. We can see it now. It took 13.8 billion years, so it's a start, it's the birth of the universe. We sort of almost see it. 380,000 years after the birth of the universe. And we get this picture, the Planck telescope. It's a picture, it's called the cosmic microwave background radiation. So it's the afterglow of the Big Bang, or what I call now the Big Pfft. And this is afterglow, so it's the light. As soon as light could travel around, move around freely, we can see that. So as the universe stretched, the light's wavelength also stretched, and I think it's in the region of 2 millimeters. We can measure this frequency of light waves. And so what you see in this picture is a temperature distribution of the early universe. So it's a temperature range. The blue and red differs by a range of 200 microkelvin. So again, it's temperature difference of the scale of 200 microkelvin. So microkelvin, that's 200 microkelvin, that's 0.2 millikelvin, that's 0.0002 Kelvin, is the difference between the blue and the red spots in this. And what makes this picture so amazing is this is the seeds of all the stars and galaxies we see in the universe today. So imagine this early universe. It's sort of a picture of the density distribution in the early universe. So we also know that, so like I said, heat is energy. You can think of heat as equal to energy, and energy in a sense equal to matter. Because of Einstein, E equals mc squared. Energy is proportional to matter. So this is density distribution of the early universe, really small scale. So the universe almost looks uniform, but it's not. There's these small random fluctuations in temperature in the early universe, 380,000 years after the birth of the universe. And okay, so what happens from here as the universe continued to expand? The denser parts, so the red parts, are slightly denser, more heat, more energy, more matter. Because of gravity, there's more matter, so gravity attracts. Where there's more matter, you'll attract more matter. So it attracted even more matter, and as the universe continued to expand and grow, denser parts attracted more and became more dense. Eventually there was enough matter in the form of hydrogen. So by now we have our first atoms, hydrogen atoms, one proton, one electron, and a lot of these attract each other. And at some stage there's enough that it kind of bursts into the first star. So this happened approximately 500 million years after the birth of the universe. We get the birth of the first stars. So enough gravity, it sort of implodes, and as it implodes it gets denser, and then it explodes again, and we get what we call, so there's enough energy for it to explode, and we get nuclear fusion. That's where two hydrogen atoms fuse together, form helium, and it releases a lot of energy. And so it's a nuclear fusion process that happens inside stars, and the first stars are born 500 million years after the Big Bang. And the universe continues to expand and grow. Okay, so now we have the first stars, and stars, it's also matter. Matter attracts gravity, so it attracts more stars, and then the stars tend to clump together in what we call galaxies. So we had different galaxies and stars, and the universe continued to expand. But maybe you'll figure out or notice that at this early stage, let's just do this again. At this early stage, we mostly only have hydrogen turning into helium. It can also happen in certain stars when its fuel is hydrogen. If it's burned through all of the hydrogen that it had, it turns it into helium now, so it only has helium left. So then it can start burning its helium. And this is a specific type of star, so Betelgeuse in the constellation of Orion. It's got this reddish, yellowish color. It's called a red giant, so it's burning helium. But we need heavier elements to form the planet, so to form Earth and ourselves. We need carbon, oxygen, iron, these kinds of elements. So where do they come from? Another really beautiful story. They are made in the guts, in the stomach of a very special type of star called a supernova. Well, the explosion is supernova. So a certain type of star will eventually, when it dies, so it's got no more fuel left, and so gravity is larger than the energy it generates. So there's more inward energy than outward energy, and this star implodes. And then again, as it implodes, there's a lot, it gets denser, there's a lot of energy, and then suddenly it explodes in the most spectacular fireworks in the universe. And this is called a supernova explosion. So it explodes in a supernova. And these stars burn to the equivalent of 10 billion stars. So it's a really spectacular explosion in the universe. And so within this, in the furnace of this exploding star, the heavier elements are made. And this exploding star, supernova, then spews out the heavier elements. So iron, carbon, these elements get spewed out of this exploding star. So there's a nuclear fusion process that's going on in this explosion with all the energy inside the stomach of the star, in its guts, and it explodes. And so stars literally die to make planets and us. We are made of these elements that form in the guts of these exploding stars. Okay, so we have these heavier elements produced in this explosion, and okay, so they get spewed out. And again, gravity, so there's this gravity attracts. So where there's a big chunk of heavier elements, it will attract more of the heavier elements. So imagine you consider as meteorites or rocks in space. Also, usually because of the gravity of a star nearby, it will orbit the star. And it will attract more rocks, more other rocks. And so it will grow. At first there's a lot of small rocks, but they will attract and grow. And that's exactly also how our Earth was born, out of one of these explosions. So just quickly, so Earth was born 4.5 billion years ago, so our Sun and Earth. Basically, hopefully you know that the Sun is a star. And there's also, it was born way back, 4.5 billion years ago. We had the Sun and our Earth, but back then the Earth it started out of also these universe rocks that through gravity attracted more and more and more. There's a quick side note here. Just the vastness and the beauty of the universe. So hopefully you can already see the beauty in all of this. Universe was born 13.8 billion years ago, and the particles, the gluons and quarks, and that was born at the beginning of the universe, 13.8 billion years ago. That's still what makes up the universe now. So what's inside you was actually also born 13.8 billion years ago. And just through these natural processes, we get all the stars. I'll get to the number of stars now, and planets and all of this And it's such a beautiful, stars died for planets to form, for us to be here. And I'm pretty sure it's more than just us being here. I mean, that's what I wanted to get to. There's 2 trillion galaxies. So they're estimating this, but an estimated 2 trillion galaxies in our observable universe. So observable universe, the birth of the universe was 13.8 billion years ago. So only light from 13.8 billion light years away have reached us now. It can be a lot larger than this. So the observable universe, we can estimate that there's 2 trillion galaxies. And every galaxy has more than 100 billion stars. Just take a second and take it in. Think about it. It's enormous. Anyways, this is a huge, crazy place. So, out of the craziness of quantum physics, these virtual particles, a whole universe was born. And everything we see, and we're a really small part of this universe. If you can fathom the idea of 2 trillion galaxies, each with 100 to 500 billion stars. But, at this early stage, back to my story, 4.5 billion years ago, the Earth was a crazy place back then, not as calm as it's now. And okay, I want to continue the story, but I'll do that in the next video. So how do you get from the birth of Earth 4.5 billion years ago, Earth, the sun, Earth, here's the sun, my golden sun, to where we are today? So that will be my next video.